recording now. Yay. You guys actually listen to recordings? Does it matter?
No, because you're still in class. We don't need to go back. It's just it's once and like.
But the dulcet tones of my sexy voice need to be re-experienced at all opportunities. Wow. All right. Well, it's recording anyway. Just to prove to people that I actually did the lecture. So you probably noticed, or haven't, that the assignments have been uploaded. Now, there is some misunderstanding. I had exercises and assignments. The exercises are just for your homework, just for you to explore. She's nodding along, I did all that. The assignments are what's getting marked. So I uploaded the 2 assignments late last night. My philosophy for grad classes is, I'm not here to punish you. You're going to do fine on it. If you don't do fine, I'll let you redo it. It's fine. Everyone's going to get an A+, all right? We're going to make sure that happens, unless you really, really screw up. And it is an individual assignment, but if you work together, I won't know. I just want to make sure. Am I recording this? Wow. So I just want to make sure that you are learning something, okay? So the first assignment is due, I think, the 10th. If that's too soon, we can change the deadline. It's not a big deal for me. And the second one is due on the 28th, which is after this module is over. But again, we can move the deadlines. I don't really care that much, okay? The first one, I've given you a data set in both SPSS version and in Excel for those of you who want to use Excel, because you can actually use Excel for this. And very straightforward questions with tables to fill in and questions to answer. I think it's pretty straightforward. It's almost the same assignment I give to my undergrads, but for them, I make them do it by hand. So for you, you just, right, exactly, because I hate them. Oh my God, I recorded that. No, I don't hate them. I adore little bastards. Sorry, I've been answering undergrad emails all morning. I was telling Kelly about it.
We all have been answering undergrad emails.
Wow. Something special's happened this year. Okay. So, moving on. So far, we have done all these, I know, annoyingly arcane and abstract concepts like distributions and p-values, things that probably gave you nightmares in high school. I get that. That's because we like to draw a distinction between what we do with continuous variables and what we do with categorical variables. And you remember the difference between those two, right? Continuous is like your age and your height and your weight, and categorical is yes, no, male, female, etc. So today we're going to take a little detour into what we do with categorical variables at a very simple level. And in addition, we're going to throw in something on correlation. So I like to call this bivariate analysis. Bivariate simply means using 2 variables to compare, right? Is something related to something else? So let us begin. The first one we'll look at is the chi-square. And I'm sure you've been exposed to this before. Everyone does it wrong. I've read papers like, really? All the assumptions are violated. It's fascinating. And it's not a great test. I don't like this test, but it's an easy test to do. And what it is really is a test to see whether 2 categorical variables are systematically related. If they were continuous variables, we would use a correlation coefficient, as I'll show you later on. But for categorical variables, like, is the employee at the service desk, does that matter in relation to whether or not the store gets a positive or negative rating? Right? So chi-square tests are done very often by businesses as a way to do evaluations, because it's a simple thing and everyone kind of understands how they work. So this is how it works. Let's say we have 150 patients with disease X. When I first started teaching statistics, I'd make up like great disease names like sore butt disease and shit like that. And then, of course, you get the complaints. I think it's offensive, people with sore butts. So I've retreated to disease X. Right? It can't be me anymore, man. It can't be me. So of those 150 patients, 42 went under therapy 1. Again, this used to be vigorous testicular massage. But again, I can't say that anymore because the culture has changed, right? So 42 undergo therapy 1, and 108 experience therapy 2, and I don't remember what therapy 2 used to be, but you can make up your own mind, okay? Some of these are cured of disease X, of sore butt disease, and some of them are not. All right? So how many variables are in this example so far? Exactly, what are they?
People who've done therapy 1 and people who did therapy 2.
Right, that's two. Well, okay, that's one variable.
Okay.
Some are cured.
People who are...
There it is, all right, see? So which therapy group you went into and whether or not you're cured. It's a challenge. So very often people who start off in data analysis have an issue identifying how many variables they are and what they are, right? Especially when it's presented like this. But if you, as you progress in science, this is how the experience will unfold. And you got to figure out exactly what am I measuring here, okay? Now, these two variables, are they categorical or continuous? Obviously, they're categorical because you're doing chi-square. And how many levels are there? There are 2 levels each. They're both dichotomous binary variables, right? Cure, not cure, therapy 1, therapy 2. I could have had therapy 3. I could have had cured, not cured, and a little bit pregnant. I don't know. Or something like that, right? So there's no limit on the categories I have here. But I've chosen a 2 and a 2. So we want to know if there is a relationship between which therapy group you're in and whether or not you're cured. The way that chi-square approaches this, it's asking, is there a difference in the proportion of who was cured in therapy 1 versus the proportion of who was cured in therapy 2? It will not tell us which one is better. It will just tell us if there is a relationship. If there is a relationship, we can dig down now and figure out which one was better, which one has a higher cure rate, because we can see that right away. But an important thing to note with the chi-square, it just tells us if they are different, not which one is higher or lower. Okay? So the chi-square test for independence tells us if there is an association between these 2 categorical variables, if these proportions are in some way related. And it's called a chi-square because this is the Greek letter chi, not an X, it's a chi. And it's a test statistic that we compute. It falls along a distribution called the chi-square distribution. None of that is relevant to you. Why bother you with math? You see my hat actually says math on the front. I'm very proud of my math background, but nobody else seems to care. So we won't go that deeply into it. But the way that we do this is we create a contingency table. This is called a contingency table. That's because the data that are on the table is contingent upon which category you're in. So it's pretty obvious what's going on here. For those in therapy 1, 31 were cured and 11 were not cured, total of 42. Those in therapy 2, 57 were cured, 51 were not cured, for a total of 108. Okay? These red portions of the table, the totals, are what we call the marginals. They're in the margins of the table. You'll see this term pop up occasionally if you read further in statistics. But the marginals are important to how we approach a chi-square. Okay? Because the way you compute a chi-square is this ridiculous formula that you don't really need to know, but I want you to understand where it came from. It's looking at the difference between the observed data and the expected data. The observed data is what you collect in your research. The expected data is what we're going to compute right now, assuming that there is no relationship between the 2 variables. In other words, the null hypothesis is true. The null hypothesis is true. There's no relationship between the variables, and the data will follow along predicted probabilistic methods. So how do we get the expected data? Well, we do it using the marginals. So if you remember, look at this box over here. Therapy 1, cured. The original observed data was 31, right? To get this one, we take the marginal of this times marginal over there and divide it by the total. This one, we take the marginal over here, marginal over there, divided by the total, et cetera, et cetera, et cetera. And the reason for that is that's the way the math works out. If there's no relationship between the 2, then that's the predicted proportions we would get given the size of the marginals. Again, you won't be doing this manually. The computer will do it for you. But I want you to understand why it's happening that way. You will be doing it manually if you use Excel. I'll show you how that works later on. Okay? So when you do that math, these are the expected values. Expected, again, if the null hypothesis is true and there is no systematic relationship between the 2 variables. If you plug in that equation, you get this number, which is the chi-square statistic. What do you do with that? Well, if you were doing this old school, back in the day, or in second-year statistics, I would make you go to the back of the textbook and look that up and compute your degrees of freedom and all that stuff. Or you can use an online chi-square calculator. Doesn't matter. You can use packages to get a p-value. Okay. So in SPSS, you do it by going to Analyze, Descriptive Stats, Cross Tabs, then selecting the chi-square option up there. And in Excel, you do it this way. In Excel, you've actually got to create the contingency tables, right? So here's your observed data, and you have to impute the expected using the approach I showed you, multiplying the marginals and dividing the totals. Yeah, get these numbers here. And then with Excel, you use that formula up there, the chi-test over there, to give you that. And that's the p-value. If you want to use Excel, as all the business types do. Okay, that's fine. Excel is great. I love Excel. It's fantastic. Or Google Sheets. That's even better because it's free. All right. So this is the p-value. What do we do with that? Is that low or high, by the way? It's low. Lower than what? 0.05, which is our arbitrary alpha level. Completely arbitrary. But we need a number, so we choose 0.05. It's low, therefore the null must go. Right on. Okay? So the null was there is no relationship between these variables. The null must go, therefore there is a relationship between these variables. In fact, therapy 1 has a cure rate of 97.6%. Therapy 2 has a cure rate of 52.8%. And because the null is gone, that's a statistically significant difference. You can tell on its face it's statistically significant. But if it was closer, you couldn't tell. Right? So the chi-square tells us that those differences are real. Yay, therapy 1. So now the businessman goes and invests his money in therapy 1 because he's proven that the evaluation works. Fantastic. That's why chi-square is so useful and popular. It's pretty easy to apply. The reason that people do it wrong mostly is that they fail to account for these assumptions. First assumption, the data in the tables have to be frequencies or counts. They can't be proportions, like the percentage of people in this group. No, it's got to be actual raw numbers. I didn't mention this, but a lot of the papers I've seen don't use actual categorical variables. They use sometimes ordinal variables, like satisfaction level with service. Well satisfied, not satisfied, moderately satisfied, versus are you willing to come back, yes or no, okay? But that first satisfaction one, that's an ordinal measurement. That's not categorical. That's not nominal. So chi-square requires that nominal category. You can get away with it, to be honest. The actual answer will probably be the same. And what do you do if it's ordinal? You use a more exotic test, actually the Mantel-Haenszel test, which I will not be teaching you. Doesn't matter. Doesn't matter. Just be aware that if it's not categorical, then you have to explore further. Next, each subject may contribute data to only one cell. Right? So each of those cells you saw in the contingency table was full with people who are not the same. Fourth, the study groups must be independent. What does that mean? That means that the same people cannot be in therapy group 1 and therapy group 2. Got to be different. Next, this should be observed. So there can be no zeros in your data, in your cell. In your data you can have zeros, but there can't be nobody populating each cell. And this one is where a lot of people fail, is at least 80%, I would argue 100%, of the expected values should be at least 5 or more. Right? So if I go back here, what does that look like? So these numbers here should be at least 5. These numbers here, there can be no zeros. If you find yourself in a situation where you get zeros or 5s, there's another test we use, Fisher's exact test. And by the way, SPSS will do that for you automatically. And the output, it'll say exact test p-value. Okay? So just be aware of that. And in the assignments I give you, I will not be that guy. No trick questions for me. Okay. Okay. Moving on to our next bivariate section. Any questions about chi-square? Pretty straightforward, right? Okay. This is probably, I'm an epidemiologist, and we use odds ratios and relative risks all the time. And you will encounter odds ratios probably in your work going forward. Let me start with an example. Who knows what a cohort study is? Excellent. Who does not know what a cohort study is? Okay, let me review them. So in general, population studies, there are 3 types of designs. There's the cross-sectional study, in which we assess exposure and outcome simultaneously. Let's think about relating smoking and cancer, smoking lung cancer. Okay, the exposure is smoking, the outcome is cancer. Okay, if I ask you right now how many of you smoke, how many of you have cancer, I would never ask that. It's a rude question. If I ask you that right now, I've assessed both of them simultaneously. That's a cross-sectional study. If, on the other hand, I follow a bunch of smokers and a bunch of non-smokers for 20 years, and I see how many develop cancer, maybe 80% in the smoking group and 20% of the non-smoking group, that's a cohort study. Because I've started with the exposure and I've waited for the outcome to manifest. Or if I start with the cancer, if I say, let's get some cancer patients, let's get some people without cancer, and I ask them, did you smoke 20 years ago? So I've started with the outcome, and I'm assessing the exposure afterwards. That's a case control. Right, so they're all based on when you ascertain the outcome versus the exposure. We can go over that later on if you care about that. But in this example, we have a cohort study. Now again, a cohort, we begin with assessing the exposure and waiting for the outcome to manifest. So we've got 100 smokers, 100 non-smokers, and we wait 10 years to see who gets lung cancer. Straightforward, right? That's your data. Okay. Now it's important how this contingency table is made up. On the left, vertically, we have the exposure, and horizontally, we've got the outcome in green. That's important, otherwise the math does not work. Also, you start with the thing. So the smoking comes first, the exposure comes first, the non-exposure comes second. The disease comes first, the non-disease comes second. That's important. If it doesn't work that way, the math doesn't work. Some textbooks reverse it and reverse the formulas just to screw you up because they're evil. But if you stick with this, the math will always work. Okay? So again, we have 200 subjects. We have 100 smoked, 100 non-smoked, and after 10 years, 85 got cancer and 115 didn't, and that's the way the data splayed out. Excellent. What do we do with this? We're going to compute a relative risk. So what does that mean? Well, a risk is really the incidence of disease in your group. That's what a risk is. So among the smokers, the incidence or risk is 75 out of 100, or 75%. Among the non-smokers is 10 out of 100, or 10%. Easy. The relative risk is the ratio of the two. So the risk of getting cancer if you smoke, 75%. The risk of getting cancer if you don't smoke, 10%. The relative risk is divide the two, and you get 7.5. All right? Why is that important? Well, it's because everything in life has some risk associated with it. What we care about is how much risk on top of that baseline a thing gives you. If I were to tell you that 75% of people who smoke get cancer, well, that's pretty serious. But some asshole might say, well, my uncle smoked for all his life. He never got cancer. Everyone says that. That's because some people will never get cancer. On the other hand, some people who never smoke will also get cancer. That's just the noise in the system. So we divide the two to cancel out the noise. And we get the relative risk. We interpret this by saying smoking increases your risk of getting cancer by a factor of 7.5. Okay? So above the baseline, you get a risk of 7. And that's actually pretty, even though this is random data, it's actually pretty close to the truth. 7.5 is in the same area. And in general, anything 1.5 or above is worth a public health investigation. Anything that's 2 or above gets my attention pretty seriously. Right? So relative risks, this is the bread and butter of population health analysts. Sometimes, oh, by the way, anytime you're dividing two numbers, that's a ratio. It's a risk ratio. Anytime you're dividing two numbers and you get 1, what does that mean? Sorry, whispering? They're equal. So anytime a ratio of 1 is given, nothing's going on, right? So a risk of 1 means nothing is happening. No effect is seen. So that'll give you a sense of, if you do statistical testing around relative risks, we're trying to measure, a null hypothesis will be the relative risk is 1. Got a question?
How do we know the risk is important? Do we have some life calculation 7.5 is the risk factor, the relative risk, but I can talk that I can think is low and you think is high. So how do we know that is
right? Yeah. So I was saying that we like to think that if it's 2 or above, it's serious, and the reason for that is twice the risk. There's no real reason for that. It's kind of like saying the alpha is 0.05 arbitrarily. We say if the risk is doubled, then we're scared, right? So if it's 2 or above, then we start to care. Yeah.
So like with the relative risk equaling 7.5 there, is it kind of the same as saying it's like 7.5 times the risk of not smoking?
Not exactly. It's close. Not exactly. That would be a trivial risk. So it's another computation they won't do today. Right. But there's a whole series of risk computations and indices that we can compute. And the way we phrase it is specific to each one, unfortunately. That's why I've written that interpretation very specifically. It's an increase of risk above baseline of 7.5. Right. Now, just because a relative risk gives you a high number, it doesn't mean that's the cause of the disease. It just means in the presence of that exposure, your risk goes up. Maybe it's because you bought your cigarettes in Chernobyl. I don't know. But who knows what the actual cause is. So all this is still correlational or observational. It's not causal. But this is the kind of information that we used when we proved that smoking causes lung cancer. You're probably too young to remember this. Back in the 80s, enormous court battles were fought to prove that tobacco companies are responsible for lung cancer. In fact, I was asked to be an expert to defend the tobacco companies. And I gave it some serious thought. And the question I asked myself was, how would I sleep at night? And the answer was, on a bed of money. but I didn't do it. Right? Anyway, I don't want to go off on a tangent too much. Okay. Now, what happens, though, if you have a case control study? Remember, case control starts with the disease and looks backwards to see what the exposure was. This is not epi class, so we won't go too deep into this. But with case control, I cannot measure risk. I cannot measure incidence because I have chosen the disease people already. I start with people, in this case, cancer, right? I start with the cancer patients that I've gone to the hospital and chosen. So it's an artificial number to begin with. It's not a natural risk. And because I cannot compute risk, I cannot compute a relative risk. So instead, we have developed something called an odds ratio. I'll show how that works instead. An odds ratio is meant to estimate a relative risk when a relative risk cannot philosophically be computed. So in this example, we have 113 people. 101 have cancer. We went to the hospital. We got 101 cancer patients. We call these the cases. And we decided we need some controls. So we choose 12 people on the street who don't have cancer. They're the controls. We look at their medical records and we find out that 13 of them had been exposed to radiation and 100 had not. So we're going to explore whether or not radiation is associated with cancer. And that's our data, right? We set up the contingency table exactly the same way. If you didn't know this was a case control study, you might want to compute a relative risk. Because I could say, well, 12 out of 13 have cancer. But I told you already that we've chosen the cancer patients, so it's not natural, it's not real. So we cannot philosophically compute a relative risk. Instead, and if I did, by the way, the relative risk would be 1.04 if I could. But I can't. Instead, we do an odds ratio. And I won't bore you with how an odds ratio is derived and what it actually means. I'll just say the quick and dirty computation is you take that times that divided by that times this. So the diagonals divided by each other. 12 times 11 divided by 89 times 1. That gives you about 1.5. Right? So relative risks and odds ratios are things that you actually might want to do by hand sometimes because they're easy. I do them by hand all the time. But again, SPSS will do them for you. When we do logistic regression, it will give us a whole lot of odds ratios, which is why it's important that I bring it up today. The logistic regression that we'll see in maybe next week or the week after takes a bunch of variables. Let's say you're a smoker and you're low income and you're female and you're been to Chernobyl, all these other issues, and puts them all together and tries to decide how much each of those variables contributes to the probability of getting cancer. And it gives you that information in the form of odds ratio. So maybe smoking gives you like a 2 odds ratio for getting cancer. Being female gives you a 1.0, no effect at all. Going to Chernobyl gives you a 7, all these things. So keep that in mind. Odds ratios are important for that reason. And again, you compute it with the cross products. The important part here, odds ratio is meant to estimate a relative risk. And you interpret it exactly the same way, meaning if it's 2 or higher, it's pretty serious. If it's 1.5 or higher, it gets my attention. You know? And when you do a computation using a logistic regression, it'll give you a p-value, and you'll know for sure is it important or not. And again, like the relative risk, if it's 1, nothing's happening. Okay? This is how we interpret it. Radiation exposure gives 48% higher odds of getting cancer. Moving on.
If you were doing a bunch of different variables, like you said, you know, female, Chernobyl, et cetera, would each of those calculations be done separately?
The way the machine does it, and by the way, you would never do logistic regression by hand, right? The way the machine does it, it actually holds everything constant and checks each variable, like many times in a row, and reduces the variance each time. So it's actually the most popular way for population health scientists to give you an estimate of the risk posed by a thing. Right? So almost every paper you will read that's population health based will do a regression analysis and say, in the presence, controlling for, that's the word, controlling for gender, controlling for socioeconomic status, controlling for age, smoking gives you this amount of risk for getting cancer. The problem is, you can't control for everything. And you never know exactly what you've missed. Okay? So again, it's all still hand waving at the end of the day. Okay, which one is better, the odds ratio or the relative risk? The relative risk is preferred by nerds like me, the epidemiologists, because it means something. It means that above baseline, this is the risk that this behavior gives you. However, we like to estimate the relative risk using an odds ratio if we cannot compute a relative risk. Now, when can we use an odds ratio? Well, as I mentioned, in a case control environment, but only when the disease, the outcome, is rare. What does rare mean? Well, it means it probably has a prevalence of like 15% or less. Okay. The less rare, the more these two numbers diverge. The relative risk and odds ratio start resembling each other less, the more common the disease becomes. So again, the rarer the disease, the more efficient this computation. So one way to, when I review papers that use odds ratios, I examine, make sure the outcome actually is rare. And again, rare is not the way that we use rare in common parlance. We talk about a rare disease, you're talking about, I know, DIPG or some of these extreme brain tumors that affect 3 people out of the country. But rare in this case is like 10%, mathematically. Okay, odds ratios. Okay. The way you do odds ratios in SPSS, the same with chi-square, descriptive stats, crosstabs. And you choose your variables. You click on statistics, and you choose risk over here. And it'll give you the right output. Okay, that's relative risk and odds. Moving so fast, aren't we? Relative risk and odds ratios. Next, correlation. Correlation does not use categorical variables. It uses continuous variables. There are many ways to measure correlation, but I will only show you one. And by show you, I will mention to you one, because we're not going to go through in this course how to compute things specifically. With correlations, what we're really looking at are 2 continuous variables. If one goes up, does the other go up? If one goes down, does the other go down? In other words, do they go like this, more or less? So things that correlate well, your age and your height up to about age 15. Okay, the older you are, the taller you are. Then, of course, your age continues and your height kind of fattens off. So this portion here is well correlated. Your age and your income tend to go up as well, up to a point that it flattens out. Okay? That's a linear relationship. There's another kind of relationship. The name of this escapes me because it's early. That's when you can do this, but everyone's going up still the same way. Okay? That's not linear. That's a different word for it. And we use a different correlation method for that too. So the methods for correlation involve comparing each data point to see if they're going the right direction, or comparing the rank of each data point. What does rank mean? If I were to correct all of your ages, for example, you're 20, you're 21, you're 15, you're 36, etc., you're 16 as well, write it all down, then I rank it, I sort it from highest to lowest. Then I also collect, I don't know, your something that's not offensive. The value of your winter coats in dollars, right? And I go, oh, $100, $1,000, $2,000 because you're rich, like whatever, and keep on going, right? And then I also rank those. And then I correlate the rankings. I don't correlate the actual numbers, the actual ages, but the rank. That's another technique. And we like to do that one sometimes when the ranges are weird or the measurements are inconsistent. Right? So the ranking correlations are actually more forgiving. But that's not what I'm going to mention today. For ranking, I'd recommend using a technique called Spearman's rank correlation. That's my preferred correlation coefficient because it tells a story better. We're going to talk about Pearson's rank correlation because Pearson's rank correlation segues into linear regression that we will talk about next week. Pearson does not use ranks. Pearson uses the actual numbers. Now that I've thoroughly confused you, let's begin. After interviewing thousands of people, I have found a strong correlation between being smart and agreeing with me. It's true. Okay. What? Chi-squared. What just happened here? What just happened here? Did I lose some? Oh, there we go. Okay, good. Okay, example. We have 17 populations. We have the number of heart diseases in each population and the average number of glasses of wine consumed. And you find, more or less, you see a straight line here, sort of? Right? There's almost a straight line suggesting that the more wine you drink, the fewer heart attacks you will have. Okay? Now, one could argue that that's your imagination. There's a human component to this. Oh, it's a straight line. Therefore, I can model a linear regression. And if it's linear, I can compute a correlation coefficient. There are techniques we can use to take the human away from it, to say, is this actually a straight line or is it something else? I could actually plot a perfect line through each of these points using a Fourier analysis or a power series analysis. We're going to talk about that. But be aware, there are techniques we can use to perfectly model your data and get an equation to describe it. But the more perfect your model becomes, the less useful it becomes, because your model will describe your data, but nobody else's data. The purpose of modeling, is to be able to make predictions, and we'll make predictions, and we do linear regression. Okay, I'm off on a tangent. So this is a correlation between heart attacks and wine drinking. That's real data, by the way. So a correlation coefficient summarizes that relationship, both the direction and how big it is. Right? So as I mentioned, the most common one used is called Pearson's product moment, or Pearson's rho, R-H-O. That's not an R, that's a rho, the Greek letter rho. Right? We write it as R sub P. I mentioned Spearman's rho as well. Spearman's uses the ranks. Pearson's uses the actual values. We're going to talk only about Pearson's. So there is a formula for computing it. Don't worry about it. In the era of computers, no one ever has to compute these things ever again. If you want to see what it looks like, that's the formula. Never look at it ever again. Just take a stiff drink and say, I never have to do this. Excellent. Right? Happy? No, you're not happy. Okay. So the way you interpret a correlation coefficient is that they range from -1 to +1. 0 means there is no correlation. So remember the relative risk, we said that 1 meant there's nothing going on. Here, 0 means there's nothing going on. Okay. That's important when we look at confidence intervals. Okay. If the number for which nothing is going on is in the confidence interval, then usually we say it's probably not statistical significance. Okay. And the sign tells us the direction, a positive correlation, a negative correlation, etc. And of course, the higher the number, the stronger the correlation. The closer to 1, the stronger the correlation. Right. Let's look at it now. So, did I say all this? I said all this, didn't I? Yes, I did. No, I didn't. Okay. Are there guidelines for interpreting whether or not a certain correlation number is associated with a certain human interpretation? Yes, there are many guidelines. If you look up interpreting correlation coefficients on the internet, you'll get 20 possible interpretations. I like to use this one. Okay? So a correlation of 0 to 0.19 says there is slight correlation, 0.2 to 0.4. There is low correlation, 0.4 to 0.7, moderate, 0.7 to 0.9, high, and above 0.9, very high. In practice, I've almost never seen anything above 0.7 in large population studies. So if I see something in the 0.4 to 0.7 range, I get very excited. That's actually quite meaningful because real life is messy. So if you see something high, it's almost a perfect straight line. Okay. So the role of range matters. Remember, range is the difference between your highest number and your lowest number. If the range of one variable is profoundly different from the range of the other variable, it will skew your correlation towards 0. For example, if you were doing the population's height in millimeters and their weight in kilograms. Height and weight are well correlated, we know that. But millimeters, your height in millimeters will be measured in thousands of millimeters, possibly tens of thousands, and your weight in kilograms will be probably less than 100. So that range is going to be quite different. By using the units alone, that will drive it towards 0. By the way, if I were to use the rank correlation, like look at who's the shortest, who's the second shortest, etc., and who's the heaviest, who's the second, and use the rank instead, that problem goes away. Okay. But we're not talking about rank correlation, we're talking about pure correlation. Right. Here's another example. The correlation between the age of a Canadian and how many children he has. So in general, older people have more kids. So there's going to be a positive correlation in general, up to a certain point. It won't be probably like a 0.3 correlation. Right? But because their maximum number of kids is probably around 5, unless you're in Utah, whereas your maximum age is probably around 100. That range difference is quite extreme, and that'll press that correlation coefficient down to 0.1 maybe rather than the 0.3 or 0.4 it should be. Right, here are some examples. -1, a perfect straight line going the other direction. 0.96, almost a perfect straight line going the positive direction. This is -0.3. Does that look like anything? All right? It could. If there was another point here, it would look like nothing. But it looks like something's happening.
You can kind of see it that way.
Yeah, exactly. So that's actually a fairly robust correlation, in my opinion. It's a weak but noticeable correlation. And that's 0 correlation. I was going to show you this other thing. I didn't bring that. There are 4 correlation plots I can show you that have exactly the same correlation coefficient. I think it's 0.7. But they look weirdly different. One's a U, one's a blob, one's because the math can't see the graph. I keep saying this all the time. The human component is never going to go away from this. The machine will be able to do so much math, but the human has to see if the math actually is looking at something real. Right, so I'm not that afraid of AI as a result of all that. But in general, that's what you're looking at. You're looking for a tighter grouping in a straight line for a higher correlation. All right, correlation and causation. We talked briefly about this last time. Popular joke. I used to think correlation implied causation. Then I took a stats class. Now I don't. Sounds like it'd help. Well, maybe. Is there a correlation between the stats class and learning statistics? I don't know. Okay, here's a classic correlation causation issue. This is real data. This is the number of shark attacks over the years in New England and the ice cream sales. So clearly, ice cream causes shark attacks. Okay. So, and there's a couple of websites that collect correlation causation data to show, like, I think one of them is imports of air conditioners from Mexico are associated with measles outbreaks in Utah, something like that. It's bizarre. It's just random correlation. By the way, do you know what's going on here? Exactly. Hot summer day, people are at the beach and they're buying ice cream. So we call the hot summer day a confounder. Confounder either masks a real relationship between two variables or creates the illusion of a relationship between two variables. So be aware, people always say correlation is not causation. Absolutely true. The correlation gives us wisdom about the universe that we then use our human intellects to peruse more deeply. Okay? Again, the machine would just conclude, if you want to stop shark attacks, stop selling ice cream. But you know, as a human being, to attach more meaning to it. All right. When the computer, SPSS, yes?
I just had a question. In cases that we know a confounder exists, there are ways to control
Yes, there are.
them, right?
Yes. Okay, here's an example. If I'm doing a study of, here's a classic one. Right, okay. Study of high school. We looked at the students in English class and the students in shop class, wood shop. We found that the students in English class have fewer breathing problems than the students in shop class. Why do you think that is? The students in wood shop have like impaired breathing and the students in shop class and English class don't. Why?
They're like exposed, like that's
That would be the conclusion, wouldn't it?
Yeah.
What's actually happening is that the students in shop class are more likely to be smokers. Right? That's true. If you've ever been to shop class, they're all smokers. Same with chefs for some reason. So, because they're outside smoking all the time. So it's not the shop that experience that caused them to have breathing problems, it's the fact that they're smokers. How would we have controlled for that? We've analyzed the smokers separately from the non-smokers. We stratify, that's called. So the classic confounders are age, sex, smoking, and socioeconomic status. The one epidemiology joke I know, which is hilarious, is what is an epidemiologist? Someone who's broken down by age and sex. Nothing? Nobody? Nothing? Come on, that's good. Because we break our data down by age and sex to avoid the classic confounders. If I were to analyze the women only versus themselves and the men only versus themselves, then I remove the opportunity for sex to be a confounder. Right? If I analyze the smokers separate from the non-smokers, I remove the possibility for smoking to be a confounder, et cetera, et cetera, et cetera. When we look at logistic regression and multiple regression, that is done automatically, right? Because those factors are held constant. Yeah, I should have added, okay, so maybe next week we'll talk more about confounding and something called effect modification. Here's an example of effect modification. If I am looking at exercise and joint mobility, and I take a bunch of people, I measure how much their knees move, and then I set them on an exercise program for a week, and I measure afterwards how much their knees move. And in general, those who exercise more have more joint mobility, except for old people. For old people, those who exercise more have less joint mobility because, right? That's not a confounder. What's happened there is age has changed the direction of my relationship. The relationship is real. Now the direction has changed. That's called an effect modification. Sometimes it's called an interaction term. So when we do regression, we need to a priori think about what the effect modifiers might be. And we have to actually mess with the equations to take care of that. That, again, is a human issue. The machines can guess, but the human has to figure out, you know what, I think old people might be a little less flexible. I keep saying this, but it's an important lesson, I think, is that you cannot take the human component out of the analysis. The machine can't do everything. So to answer your question, yes, you can control for these things. A big part of this is, before you do the analysis, asking yourself, what are the likely confounders? So you can avoid a lot of analytical pitfalls in how you design your research, which is why it's important to speak to a statistician or an epidemiologist before you collect your data to make sure that you're not introducing opportunities for confounding, or at the very least, collecting the data that will allow you to identify the confounders when they appear. A very famous case of confounding. This is back in the 80s. I remember reading this when I was a student. A study found that drinking coffee is associated with pancreatic cancer. Okay? And they did this using a case control study. What's a case control study? Work backwards, exactly, right? So they were actually, so what they did was they found some pancreatic cancer patients, and they found some non-pancreatic cancer patients, and they asked them how much you drank coffee in the past 5 years, and they found a very strong signal, odds ratio, between those who had pancreatic cancer and those who drank a lot of coffee. The problem there was how they chose the cases and controls. Because remember, you had to choose, go to the hospital and choose. And if you're clever, you choose your controls to be as similar as the cases as possible, except for the thing you care about, in this case, pancreatic cancer. So they went to the hospital, and they found the pancreatic cancer patients, and they asked themselves, who can we choose as controls now? Well, who has the same lifestyle, who probably has the same doctor, the same diet, same age? Well, let's find other people in the same ward who don't have pancreatic cancer. And they chose people who have gastrointestinal issues from the same ward, because the hospital, they house these people together. Okay? So people with gastrointestinal issues do not drink coffee. So artificially, they suppressed the amount of coffee that their control group was drinking. So in their analysis, it appears as if the pancreatic cancer group was drinking a lot of coffee, but they weren't. They were drinking a normal amount of coffee, just the controls were really low. So in that case, gastrointestinal issues was the confounder. Okay, it can really mess up your studies, and that was a famous study in the Lancet, I think it was. So there it is. All right, back to correlation. When SPSS does correlations for you, you can put in any number of variables. I want to correlate age and height and weight and the price of my coat, et cetera, et cetera, et cetera. It produces a matrix like this. And the matrix has all the variables that you put in on this side and all the variables on that side, exactly the same variables. And you just read across to see which ones are correlated with which ones. So variable A has a perfect correlation with itself, obviously. Variable B has a perfect correlation with itself, obviously. But A and B have a correlation of 0.82. I could put a 0.82 over there as well. It's the same relationship. But we don't bother because we only care about it once. So SPSS will give you this half matrix like this. And the way you read it is you just find the thing you want to correlate with, and you go across, and you say that. Right? So that's how you read those things. Yes?
Is it different to say correlation between A and B, or between B and A?
No, they're exactly the same. Exactly the same. Good question. Yes?
What do those negative values represent?
They represent the relationship goes in the other direction. So I can say the more I eat, the more likely I am to be fat, right? That's a positive correlation. I can say the more I exercise, the less likely I am to be fat. That's a negative correlation. Okay, so SPSS does it this way. Analyze, correlate, choose bivariate, and then you choose the things you want to correlate, press OK, and this is the output. Now, this is a correlation matrix. There's only two variables here. Height is perfectly correlated with itself. Weight is perfectly correlated with itself, and this is the actual numbers. Height and weight have a correlation of 0.5, which is very good. Now, what we have here is the ends, how many people were in that analysis, but also the p-value. It's not really 0. There's only so many digits. It's just less than 0.001. A lot of people report the p-value for correlations. I don't think it's necessary. So remember, a p-value gives us the significance of the null the probability of getting this result if the null hypothesis were true. The null hypothesis in a correlation is that there is zero correlation. So it's clearly not, it's almost never zero. So to me, it's kind of irrelevant. So I never really care about the p-value for a correlation. It doesn't mean a whole lot. What I care about is the actual correlation number itself. 0.5, that's very high. But there's a magical thing that happens if you square that number. If you square the Pearson's correlation, does anyone know what you get?
There's variance or something.
Close. You get the percentage of variance in the other variable that your variable explains. I'll say it again. You get the percentage of variance in one of the variables that the other variable explains. So in this case, 0.5 squared is like 0.25. It's 50%. 50% squared is, oh, yeah, is that right? 0.5 squared is, it's 2.5? I don't know. I can't do math in my head anymore. Right, so that gives us, let's say it's 2.5. 0.25? Someone do the math for me. Is that right?
What do you want to square?
0.5.
0.5? Yeah, 0.2.
Is it 0.2 or 0.0025?
Wait.
People listening to this right now, yes. It's 0.25? Seriously, it's not 0.02? Okay, interesting. All right, so 0.25. So essentially we're saying for this correlation, even though it's a strong correlation, only 25% of the variance in height is explained by weight and vice versa. What explains the rest of it? What explains the other 75%?
The other variable?
Like what?
Sex, maybe?
Everything else. Everything else. Okay? So it's tempting if you have a strong correlation to say, oh, height and weight, that's an obvious one. Right? But let's say it's the signal I get from my test based upon this new drug that I brought in, or the reduction in tumor diameter as a result of this drug. It's tempting to say, well, I got a 0.5 correlation. Clearly my drug is working. Your drug probably is working. But it's only accounting for 25% of the fuzziness in that data. What's accounting for the rest of it are the other factors. So when we do multiple regression, we're going to do a different kind of correlation coefficient that tells us how much variance is explained by all the variables in our soup. I keep calling it a soup. It's a soup. It's a soup full of ingredients. And these ingredients are variables. Right? So if I'm trying to predict height, weight is a very good predictor of height. It gives me 25% of the variance. Maybe I can throw in sex, because the men will be taller, the women will be shorter. They'll add another 5%, let's say. Then I'll throw in ethnicity, because some ethnicities are taller than others. That adds another 1%. Then I'll throw in wealth, because rich people eat better food and they're taller. Who knows, right? So I can throw in variables to add a little more explanation of the variance. That's all I'm saying. Is that my last slide? I think that's the last. What a fast lecture. Wow! I should have brought more today. So I can never tell how much stuff I'm going to cover. It's a mystery. Ask me some questions about anything in life. Yes.
Well, it's not anything. You mentioned something about the unit, changing the unit can affect the correlation.
Right. Yes.
So can we modify, so if we don't see a correlation, can I just change the unit so we can see a correlation?
To a certain limit. I mean, not really. It'll change the correlation lower, right? If it changes the range. That's all. But the closer you get the ranges to match, you will max out your correlation. Okay. So there's an upper limit. Yes?
So, kind of like maybe like a long-winded question, but bear with me, please. So, for my specific research, we're trying to...
Me. Go on, sorry.
Listen. We're trying to figure out if we can do two different residential homes, and the one we can use as a control versus an intervention, right? But I think that there's certain confounders within that, because not all residential homes work on the same ethical values, et cetera, et cetera.
Okay.
Some of them are pretty crappy. There's no way to control for that, is there?
Yeah, you can. If you identify the confounder, you just analyze by that factor. So let's say the confounder is ethics, and you can measure if one is ethical, one is not ethical. You just analyze the ethical ones separate from the unethical ones. Hey, see, it's not that hard. It's not that hard. Again, for those of you who missed my early spiel, we talked about the assignment, and there was some confusion about the exercises versus the assignments. The exercises are there for your own erudition. Just do them or not. I won't see them. The assignments were uploaded very late last night when I was feeling energetic, and those are for marks. And I'm not a picky marker for grad classes. I'm not here to punish you. If you struggle, let me know. If you want to do it again, you know what? I even let you upload many times and take the most recent one. I don't care that much. So I just want you to learn. So don't freak out about it. But it's uploaded right now if you want to try it out. As I mentioned, it is an individual assignment, but I won't know if you talk to each other. So, all right. More questions? Lay it on me. Yes. No. Yes, what? Yeah, because I should have had a Spearman slide. I didn't think I'd have time. So the way Spearman's is essentially the same as Pearson's, except done on ranks. So let's say we're correlating weight and height. So Spearman's, we've got the actual. So Pearson's, we have the actual weight and the actual height in centimeters or kilograms, whatever it might be. So let's say instead I looked at who's the tallest, and I gave them a 1. Who's the second tallest? I gave them a 2, blah, 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 down to the 408th tallest, and gave them a 408. And if I take the weight, who's the heaviest? I give him a 1. Who's the second heaviest? Give him a 2, down to the bottom one. Then I do a Pearson's on those ranking numbers. Question?
What happens if someone's the same height or the same weight?
Ah.
How do you
Yeah, there's actually a technique for that. So you give them the same number. Yeah. That's right. All they care about is the ranks. What that does, it takes care of the outliers. Right? Because the distance between ranks is always the same. Outliers are. So maybe the heaviest guy is 3,000 pounds, and the second heaviest is 150. Right? So here, that would really skew things. But in the case of the ranking, it's just one more number. Doesn't matter. Yeah. So ranking is more robust, meaning it's more forgiving to issues. But it does not convert well to linear regression. And we're going to do linear regression next. And I was hoping for a clean segue there. Yes?
For multivariate analysis, is there a different method to follow? Or do you take bivariate?
Okay. For multivariate methods, yes, they're different approaches, but they evolve from these approaches. So let's look at linear regression, for example. Linear regression, as you will see next week, as you have done before in high school, is the same as a correlation, except weight and height are correlated, we see here, but can I predict weight based on height? Can I write a straight line equation, like y equals mx plus b from high school? Right? I probably can. But let's say I had another variable as well, weight, height, and age. Can I have a third variable there? Yes, I can. It's not a line anymore now. It's like a plane. It's 3 dimensions. It's a plane, not a line. If I throw in a fourth variable, like wealth, now it's not even a plane. It's a multi-dimensional construct, which is why I love this so much, because you're actually literally playing in multi-dimensions. It's spacey stuff. You will be traveling in multiple dimensions next week. How cool is that? So it's the same idea. It's just at different levels. And the R, the Pearson's correlation coefficient here tells us, if I square it, the amount of variance one variable explains in the other. For multiple linear regression, it's a different R. It's a capital R, but it does the same thing. I square it, and it tells me how much variance all these soups, all the ingredients in the soup give me, right? For the plane, for this multidimensional plane. The difference, though, is that doesn't go from -1 to +1. It goes from 0 to 1, because nobody knows what minus numbers mean in multi-dimensions. Right? So same idea.
And also, so on SPSS, where would you go?
Well, you'll see that next week, but essentially it's probably the general linear models, I think, if I remember correctly. Could be wrong. We'll find out next week. Yeah. That's for multiple linear regression. For logistic regression, it's much different. Logistic is when we are trying to regress not to a straight line, but to a yes-no. Like, what are the factors that are predictive of having this disease, yes or no? Or the factors that are predictive of passing this course, yes or no? So I will compute odds ratios. What's the odds ratio of being female and passing this course? Odds ratio of being like short and passing this course, that kind of thing. We'll also do ANOVAs the next week, the week after, and ANOVAs are like t-tests, but they look at, are the means of a variety of things different or the same? The example I always give is, if you want to compare the mean mileage of 2 makes of car, I'd use a t-test. Pretty straightforward, 2-sample t-test. If I want to compare the mean mileage of 2 makes of car from 2 different factories, well, now I've got 2 variables in play there. I've got the car and I've got the factories, right? That's complicated. If I want to compare the mean mileage of 2 makes of cars in 2 factories in multiple cities, well, now I've got 3 factors going on. It gets complicated. So the ANOVA allows us to stratify that analysis and tell us, are these averages different or not? Yeah, I'm off on a tangent again. To answer your question, it's different, but the concepts are similar. More questions, lay it on me. We have a little bit of time. If not, we could end early. Yes?
I feel like this is like possibly a dumb question. But
I always say there's no such thing as a dumb question, but there are. Go on.
For R squared, like I've memorized like R squared is like the amount of variance y divided by x, and like that's fine, and you can memorize that and
What does it mean?
answer a question. But like, what does the variance have to do with?
Okay, remember that variance is the width of my distribution, the fuzziness of my distribution, how precise it is in some ways. And a distribution in height in a sample is interesting because, oh, some people are short, some people are tall. That's interesting. Why are they tall? Why are they short? Is it because there's errors in how I measure them? Is it because I just sample them poorly? Or is it because there's something intrinsically interesting about these people that maybe I can predict? So if weight is responsible for 25% of that, oh, then I know that that's probably the biggest contributing factor to why I've got so many different heights in my sample. Maybe there's some other factors I'll explore afterwards, but 25% is actually a pretty big chunk. Wow, that's a good answer. Nice.
Kind of like how much I can say like that variable is not causal, but like that
That's right.
variable is related to.
That's right. Okay. Yeah, I mean, it's a delicate little dance with the language because you're tempted to say, well, I've explained it away. Then it's just the way the numbers splay on a systematic basis. This one splays along with this one at this rate, so it seems likely that there's a relationship. But again, the human component has to step in and say, does it actually make sense? Because sometimes it makes no sense. In which case, you retreat and say, the numbers are telling me nonsense, which is fine. Nothing? Oh, I'm going to end early, and that guy's going to be freaked out because he's going to show up and the class will be empty. I got to time these things better. Like the first class had too much stuff. These last two, too little stuff. All right, done. Nice. Next class is the 3-hour one, right? That will not be here. That will be in Thompson. We will send out a reminder of which class it's in.
Like the entire thing?
The entire thing, yes. Yeah, because that guy will come back. It'd be funny if he shows up there.
He was so salty with us last week when we were leaving. He's like, okay, come on. And he said something in Italian, didn't he?
Oh yeah, he was like bravo ragazzi, and I was like.
Wow. That's amazing. There's like a